All right, a couple things on here that you need to know. We are not going to be going over. We're not going to be going over molecular orbital theory because it's no longer MO theory. It's no longer on the AP exam. All right, but moving forward, we got to kind of know everything that we've already been talking about, which is good for us. So we've already been talking about all this. We're going to talk about three models. All right, one, the valence shell electron pair repulsion, which we have already talked about quite a bit. So that's the valence shell electron pair repulsion. Valence shell electron pair repulsion. Okay. About why the molecules form bonds and why they have the shape they do. Valence bond theory. A little bit about that. This one is canceled. You don't have to know this one at all. All right, we're not going to waste time on it. Why would we waste time on it if it's not on the exam? We will not do that. All right, so that is gone. All right, so you do not have to do that. All right, that changed about 2 or 3 years ago. Okay, so we're not going to do that. But we need to know why it's going to form the shape that it does, explain it, know the hybridization, and so forth. Okay, pretty simple stuff. We already are going to find out that we know most of this stuff. Bond angles, the angles made by lining up by lines joining the nuclei of a molecule's atoms. All right, we have 3 of them. What do you think this one would be? Anybody have any idea what this could be? What is it? Yeah, the actual molecule. Not water. CO2. All right, what do you think this one is? What's the name of it? Methane. So if you see methane, you have to know that it's CH4. That is the sight word that you need to know. All right, we'll also talk about meth, eth, prop, but, all those things in a little bit, but not today. All right, you will know those. It'll be done. You'll be easy with this. And the last one we have is CH2O, which is formaldehyde. What do we use that for? That would use formaldehyde for mouthwash. Formaldehyde's used for so probably don't really want to use that for cleaning or mouthwash. Those 2 things, probably not good. All right, so this has 180. What do you think methane has? Let's see if you know. All right. Oh, sorry, 120 and 9. Very good. Why is the other one 120? All right, so what do we have here? We have A. X3. I don't see any lone. I have A. What is the shape of that? Trigonal. Planar. All right, trigonal planar. All right, and this one is, what's the shape of this? Tetrahedral. All right. What about this? Linear. All right. So you have some of the pretty good ones. Moving on right now. Okay, so Vesper. So electron domain. We're going to talk about those a little bit. A region in which at least 2 electrons are found because they repel each other. Because why do you think electrons are going to? They don't like each other. They're all negatively charged. They're all negatively charged. Bonding domain, 2 to 6 electrons. They're shared by 2 atoms. All right, they are going to form a covalent bond. Non-bonding, 2 electrons are also called lone pairs. The E's. All right, we're talking about the E's. We're talking about the X's, and we're talking about the A's. All right, so we're talking about A's, the X's, and the E's. All right, that's how we classify it. So we are successful on the exam. All right. So non-bonding. For ammonia, there are 3 bonding, 1 non-bonding domain. So let's try, what's the formula for ammonia? All right, NH3. All right, so see if you can draw that right here for me. If you can draw that ammonia for me right there. Go ahead. Never mind. All right, I'll never mind. All right, NH3. All right, Leah, what do you have? Uh-huh. Okay, and one pair. Okay, have that? What do you think the bond angles are? Okay, so you would think, so you did AX3E, right? That gives you 109.5. However, one lone pair, you take away 2.5 from angle. So the angle is going to be 107. So I want you to keep that in mind for later. So we're going to go over a couple other ones, and maybe that'll change it. Every time you add a lone pair, it decreases the angle by 2.5 from a tetrahedral. Okay? Pretty easy to remember. What's that? Yeah, you'll see. All right. All right. So we have this. Okay. 4 electron domains. So we do have an electron domain of tetrahedral, but we have a shape of what? What is the shape of that thing? What's the shape of that? Trigonal pyramidal. All right. They're going to arrange themselves to minimize their repulsions. So what is this saying is this guy is big bad. He's going to push everybody away. All right. He's going to push everybody away from it. And it's going to decrease those angles. Okay. All right. Okay, let's get into some good stuff. All right, electron domain geometry is one of the 5 basic arrangements of domains. Depends on total number of electron domains. Describes the orientation in space. Depends on each kind of electron domain. All right. And, okay, so if we just take a look at that, boom, there's a couple examples. All right. Okay, so we have this. Oh, we already know what this may be. What do you think this may be? I don't know. COF2, I think, something like that. All right, now we got phosphorus, what? Pentachloride, sulfur, hexafluoride, all right? Sulfur dioxide. Right? So we have a bunch of those that we already know how to do. So we're not going to have, there we go. Let me pop up. Examples of these are very common. Usually, these are the ones that are used most of the time on an AP exam. A trigonal planar boron trifluoride, a bent nitrogen dioxide, a tetrahedral, all right? Methane, trigonal planar, pyramidal ammonia, which you already told me. And then we have water. So water, some of you have been cringing probably every time we said that the angle is 109.5. It's not 109.5. Somebody tell me what they think it is. It's not 107. All right, let's. So we started at 109.5, and this has AX2E2.
So minus 5.
104.5. Okay, that is the accepted correct. I think they'll accept 105, but you should already know it now. It loses 2.5 when you add a lone pair. It's pretty easy to do. All right, trigonal bipyramidal. A couple examples: phosphorus pentachloride, a linear xenon difluoride, a seesaw sulfur tetrafluoride, cape chloride. These are all seeing on the exam. It's kind of crazy. Octahedral, all right, SF6 for hexafluoride, square planar, square pyramidal. Now, what happens as you increase domains? As you go down, what happens? What happens compared to over here? All right, so God bless you. If there's 5 domains, 5 domains equals 4 possible geometries. All right? So you should see the pattern. If I went up to 6 domains, there's going to be 5. All right? There's more than that. You'll see them. All right? You'll see them. There's more than just that. But for what we're doing, these would be the maxed out. All right? Most of the thing is hybridization. They don't even really, on the AP exam anymore, include the dehybridization. All right? So the biggest one you'd have is SP3. Okay, well that's easy. But just in case, we learned SP3 and the Ds as well. All right? We always want to know that. Octahedral, nice to know. Let's take a look. Trigonal, bipyramidal, tetrahedral, trigonal. I don't think we have many issues there. All right? Any issues with that? No. All right? We just have to memorize. We have to know. We've already memorized once. We just have to make sure we can put pen to paper. All right? Moving on. To find the electron domain geometry, the molecular geometry, and the molecular geometry, draw the Lewis structure. Okay, so let's go ahead and predict the electron domain geometry and the molecular. So let's go ahead and let's do this one together. The first thing I'm going to have to do is what? All right, total electrons. All right, so for tin, we're going to go by what group it's in. Even though tin can technically take 2 plus 4, we're only going to go by the group number. All right, so I want to put a little star here just in case. Only go by group number. Because some of you are saying, oh, wait a minute, tin can be a plus 2 or plus 4. In this case, if you're doing geometry, only go by the group number. So we got 4 plus 7 times 3 plus 1. 25 plus 1 equals 26. All right, so we have 26. Tin is definitely going to be in the middle here. What am I going to do? All right, single bonds. We'll check it out. We'll check it out. We use a whopping 6. We got 20 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, crap. Oh, no. I have 2 electrons left. All right. 2 electrons left. What? Oh, where do we put it? Where do we put it? On the top. All right. On the top. Well, that reminds me of what? All right. That reminds me of AX3E. Okay, so at this point, let's do the electron domain geometry. All right, so that means that's your total. That's your total. 4. So what is it going to be? Tetrahedral. Tetra. All right, and our molecular geometry is going to be trigonal pyramidal. All right, we're not done yet because we are rock stars and we all already know this. What is the angle going to be here, Raina? What's the angle? Okay, close. All right, so let's do this. Let's do it together. I'm glad you said that. 109.5 minus 2.5 equals 107. Perfect. All right, I need somebody to give me the hybridization of this sucker. 1, 2, 3, 4. SP3. All right, SP3. Okay. Any questions? You should be able to do that stuff. All right, so we're going to do, we got a whole bunch to do, which is great. All right, which is great. All right, O3, which if you ever come across this in your studies, is actually ozone. Okay, ozone is O3. We got to do some total electrons for that. What do we have? Okay, so I'm going to take my O. I'm going to put an O in the middle. Is that all right? Anybody disagree? Can I put O in the middle? All right, O in the middle. And now I have 14 left. 14. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, well now it looks like I have to have a lone pair left on there. But we have a problem. What do we have a problem? Oh, I'm sorry, I didn't also finish this one. What, you guys, come on now. All right, you got to do that. I don't have an octet. What am I going to do? Yes. Make double bonds. All right, so let's do this. Let me see if I can do this. All right, so I'm going to take this guy off. I'm going to move him over here. Take this guy off and move him over there. How's that? Then I'm going to take this. I'm going to do this. That good? Okay, so now what do I think immediately? What do I think about this thing? Resonance. I got to think resonance. All right. Shout out to all my peeps in Damascus watching this right now. I know you're way behind, but that's okay. All right. Resonance. I'm just saying. All right. So this is going to get eliminated here. And we're going to take this and make the double bond on this side and the single bond on this side. All right. Okay. So now we're going to have to figure out what the heck the shape of this could be. All right, what the heck the shape of this could be. Do you want to check this, though? Could we check this for formal charge? Why don't we check that to make sure that this is correct? Do you have a question? Well, let's check it for formal charge first. That's why I'm going there. All right, so let's check formal charge. All right, we can use either one of these because they're going to be the same. It doesn't matter which one you use. So see if you and your neighbor can come up with formal charge on these. All right, formal charge. And I'll just we'll put it in black. We'll put it right here, and right here. All right, formal charge here. All right. All right, Garcia, talk to me, girl. What do you got going on here for formal charge? -1, perfect. What do you have for the middle? What? 1. And what do you have over here? 0. All right, so that's going to be the same throughout, right? Everybody agrees that's going to be the same throughout. All right, let's just check it real quick because we wanted to do this, right? We wanted to try this. All right, what do we have for formal charge on that? What do we have up here? What do we have for this one? 1, 2, 3, 4, 5, 6. 6 minus 6, 0 equals 0. What do we have here? Oh, crap. So that immediately eliminates this because of this -2. We have a 0, a -2, and a 0. It doesn't matter. If these are 1s and 0s, it's better. Okay, we're good with that? Make sense? Yeah? A 2 trumps a 1 all day of the week, every day of the week. Okay? All right, so we're good on that. We got resonance. We got this. What's the angle of this thing? Mayho, what are you thinking here for this? A what? AX2 what? E, AX2E. All right, now that may not be 180. So what is the EDG? I have 3 things, right? I got 3 things here. So what is that going to be? Trigonal? Planar. All right, what's the shape? The MG. MG, AX2E is going to be bent. All right, what angle is it going to be bent to? Got it. All right, 117.5. All right, 120 would be acceptable on the exam. 117.5 is correct. But 120 is acceptable. It'll give me a range from 117 to 120. Or probably, 120 would be the max. 117 would be the least. Okay? All right, so very good. Got that. Hybrid P2. All right, perfect. All right, let's try the next one. SeCl2. What do we got here? Total electrons. 6 plus 14. 6 plus 2 times 7, 20. All right, let's put that SC in the middle. All right, now this is how you should be moving, this quickly. All right, you're looking at, you want to get these points so you can focus on the ones that are harder. All right, trust me. All right, minus 4. I got 16 left. 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we don't have an octet yet, but I have 4 left. So technically, they're going to go like that. It's going to bend these suckers down, right? Not like that. Not like that. Not like that. Like this. Uh-huh.
So when you have extra electrons, you use them as one, but when you don't have
You make that's correct. All right, that's correct. All right, so we did this. So like if you don't have enough on the central, then it becomes multiple bonds. All right, yeah, so it should be just pretty clear almost to this point. All right, so I got, all right, so that means I have my EDG being what? Tetra. All right, yeah, tetrahedral. I have my Mg being, my angle being, yep. 104.5, my hybridization, sp3. All right, sp3. Okay, we're rolling. Now you're going to see as we go on, the notes are going to talk about hybridization. You already know how to do it. The only thing we really haven't covered yet are sigma and pi bonds, which we're going to cover. Those are so simple. So simple. All right, so simple. Another one or two. We got a couple more, I think. Okay, let's just, all right, yeah. And, oh, no, carbonate. Carbonate, okay, has a minus 2, so we got to know that we have to go through back, and we're going to have to add those 2 electrons on at the end. All right, we should be getting good at this. Ashna, what am I going to do here? Uh-huh. All right, there we go, there we go, there we go. I happen to use 6. I have 18 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, well, that's nice. But no, it's not nice. What happened? What do I have to do? Ah, yes. I'm going to have to take 2. Let's just take these 2 because I want to. This one and this one, move it there. Now I have completed my octet on the carbonate. But now I have to think that I have what, George, your favorite word? Resonance. All right, now I got resonance. So boom, I'm going to go ahead and just double bond here. Oops, not that. I'm not going to do that. What did I do? What's that? It would ask you to draw it, or it would be a multiple choice type question. Most likely draw it. And drawing it should be like, oh, I can do that in like 2 seconds, right? All you're doing is moving the double bond. All right, boom. 2 minus. All right, I got 1 more left. You're probably already done. You're waiting for me because I'm slow. It's hard to do it. Sometimes it doesn't work out exactly the way I want. All right, so you'd have to have all 3 of those. 2014, you had to do all 3 of those on the exam. Okay, it's 2018. Do some type of. Let's talk about the shape. All right, let's talk about the electron domain geometry first. For this, I have A what? AX3, which equals trig plane. All right, my shape, trig plane, so it's going to stay the same. My angle, exactly 120. All right, perfect. You getting there? Getting there? Getting square? Oh, wait, it's not square planar. I'm sorry, it's a trigonal planar. Only one person got it, thanks. 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 All right, thanks. All right, so again, see how it just says resonance right here. I drew them all for you. All right, Shavitika, how many total electrons here? 6 + 7 × 4, which is like 34. Do you think? Yeah. All right, so let's go ahead and do that. All right, so I lost the fight in 8. I got 26 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Clap. No, I'm not going to add a double bond. Okay, a lone pair. So I got to kind of shift this. This guy's not going to be there, really, right? He's not going to be there. Go like this. They're going to go away from that. All right. Now, I want to make sure you understand. You don't necessarily get it wrong if you don't draw the shape. You have to know what the shape is. But you don't get it wrong if you don't reshape it like this and you did it and you just put these two there. It's not wrong. It's not wrong. Okay? You don't need to reshape it. But for us, we'll go ahead and do it because why not? When in Rome. All right, so I need some help here from Kimberly. Kimberly, what do I have for an AX? What am I working with? What am I working with here? Okay, flipping the paper. Flipping the paper. AX4E. All right, so what is my electron domain geometry then? Trigonal bipyramidal. Bipyramidal. All right, trigonal bipyramidal. Okay, what is my MG then? Seesaw. Look at it. It looks like a seesaw, right? Looks like a seesaw. All right, Ashna, what's my angle? 90 and 120. No. You could, but 90 and 120 for that. At that point, you don't have to do that. 90 and 120 is entirely correct. And my hybridization, Ashna? SP3D. Perfect. Okay, perfect. Yeah, I would not at that point subtract the 0.5. More of it for the tetrahedral ones are the ones that are most important. You'll never be tested outside the box of that. The angles that I gave you are the ones that are going to be. Okay? It's a good little side note. Okay, moving on. All right. Oh, yeah, we got it right. IF5. All right, Mayho, talk to me. How many valence electrons do I have there?
42.
All right, what am I going to put in the middle? All right, here we go. Let's try this. I'll just make it some monster like this. All right. Ooh, I used how many electrons? I used 10. Minus 10 gives me 32 left. 1, 2, 3, 4, 5, 6. I always count them. I don't know why. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Woo-hoo-hoo! Nice. Liking that. Did I do it wrong? Did I do it wrong? Oh, it's supposed to be 32. Oh, darn. All right, darn. You know, I keep doing the same thing in my honors class when we're doing like reactions now. And so like we have this reaction. I'll just a little side note here. We have this reaction, and I have students that do this. IMGCL. So I wrote OMG. OMG, really? You know, I have one student, 1 out of 67 that is just smashing everything together because I told him that, right? Sometime. All right, so I got 30 left. I'm going to put that on there. AX5E. Okay, well, what do we have? That Jeffrey. I need the domain first. Octahedral. And you already told me it's what? All right, I need to know some angles. What is the hybridization? Okay, would be the most maximum one you'd ever have, sp3d2. I really think the hybridization only goes through P now, but you know how to do it. It shouldn't matter. All right, last one you're going to try on your own, yes?
Would the angle for the last one, if it was over the pair, be 7.5, or would it still be?
Like I said, don't worry about it beyond the individual ones. Okay. Technically, yes, but don't worry about that. All right, try that one on your own. CL3, CLF3.